Alright, so for this example, it looks very similar to the example before. The only difference is I have u differentiated by x. Now, what does that mean? Well, I explained in the previous case, you have a one-dimensional rod and it's insulated in the radial direction. And the endpoints were touching ice, that's why we had the derivative, the value of u fixed to 0. But imagine that this side is also insulated. Okay, then, huh?
All four sides.
Yeah, everywhere it's insulated.
There is no change in temperature?
No, there will be change in temperature because the heat can still transfer inside the rod.
Okay.
Right? So the heat will spread out. So let's just think about what's going to happen with this initial condition. By the way, if you draw the graph of 2x minus x squared, it will be like that. The heat will dissipate, so this will go down, right? And it's going to go down, but then something is happening at this end. See, the heat here, the heat will flow over here, right, to the boundary because it's lower. But then because it's insulated, it's not going to go to 0, but the heat that flows in here is going to raise the temperature here. You get that? So the heat evolution after a little bit of time will be like a bit more flat, but it'll be like that. This endpoint will be raised slightly, right? You see that? Okay. So eventually, the equilibrium will still be a straight line, except that the equilibrium solution will be not the 0, rather it will be the average temperature. So like if you had the initial condition like this, and then you compute the average temperature of all the heat distribution here, then that will be the equilibrium solution at infinity. That's what you're going to get. Do you agree with this assessment? All right. So, in between, how do we express when heat is not escaping through the endpoints, but actually like it's just accumulating? Okay? If it accumulates, then at the end, it will be like, it will have a 0 derivative at the end. Because if it doesn't, then something doesn't make sense. See, if you had higher derivative here, what does that mean? There will be heat flowing into it, right? That doesn't make sense if it's an insulation. If you have a lower derivative, that doesn't make sense either because that means the heat is going towards it. So when you have insulation, the moment when the heat is accumulated, immediately the boundary condition will be such that the derivative or at the endpoint will be horizontal. That's how you express insulation. Is that okay? So this condition here, this is called the Neumann condition. Neumann boundary condition. And I forgot to name it, but the one without the x is called Dirichlet boundary condition. So that's the boundary condition that was first used. People were studying that first, but then later Neumann came up with this boundary condition for the case when it's insulated. Right? Okay, so let me now explain how to solve this one. You solve the same exact way. You solve, you find the building blocks for the first two parts, and then take the infinite linear combination of them, and then you let the initial conditions hold, which will give you what CNs are. Okay, and that's the idea, right? So it's pretty straightforward. You have u equals to xt, where x is a function of x only, and t is a function of t only. And if you plug that into this left side, you're going to get xt prime equals to 0.2 x double prime of t, right? Now what do? Divide everything by kxt, right? But our k value is this 0.2. The 0.2 xt. Okay? Xx cancels. t cancel, 0.2 cancel, so you have t prime over t times 0.2 here equals to x double prime over x. Okay? And then we made an argument, right? This is a function of t only, you have a function of x only. What does that mean?
It's constant.
It has to be a constant. The only way that a function of t can equal to a function of x is when they're equal to a constant, and we decide to name that constant as negative lambda for the reason that we want to obtain the Sturm Liouville. Okay? Now, the boundary conditions here, let's see what ux 0t means. That's like you differentiate x once, and then you plug in 0 and t, and that has to equal to 0. And since you don't want trivial solutions, you need x prime of 0 to be 0. Right?
Right.
And the same way, this other one will give you x prime of 2 equals to 0. Okay? With x, this one here, if you rewrite it, this is x prime plus lambda x equals to 0. Again, the Sturm Liouville problem, or the eigenvalue, eigenfunction problem, you're looking for non-trivial functions which satisfies these boundary conditions, satisfying this differential equation, and we know that they don't always exist. They only exist for certain values of lambda, right? We solved that as well. What was our answer for that? Lambda equals to n squared pi squared over 4, with our eigenfunctions being what? Cosine n pi over 2x. That's what we got, right? That's the case when you have a primes at the end. Okay? We did this also a few questions ago. Okay? But this time n starts from where? 0. Okay. Okay. Now you plug in this back in here, and you get t prime over 0.2t equals to negative lambda, and lambda is n squared pi squared over 4, so that t prime is negative 0.2 n squared pi squared over 4 times t. What's the general solution for that? If it's some constant times t equals to t prime, those are exponential functions, right? So that's c times e of this thing. Okay. And now you put everything back again, you plug it into uxt, u equals to xt, so u must be some constant times e. So negative 0.2 n squared pi squared over 4 times t times cosine n pi over 2 x, where n starts from 0 now. Okay? Now, when n is 0, look what you get. If n is 0, you get e to the 0th power, which is 1. Cosine 0 is 1, so you just get a constant, right? So we see that the simplest solution that satisfies both the heat equation and the boundary conditions are constant functions, which is true, right? If you put in constants, any derivative will give you 0, so it still satisfies this. And because this is a partial with respect to x, if you take a constant and differentiate, it does satisfy the boundary conditions as well. Okay? So when you take linear combinations, you don't want to just say sigma of this, you really want to say u is equal to c0 for n equals to 0 plus summation from n equals to 1 through infinity of cn e to the negative 0.2 n squared pi squared over 4 t cosine n pi over 2x. Okay, so that's the general solution. That's the end of step 1. What's step 2?
Finding CN.
Huh?
Finding CN.
Yeah. How do you find Cn?
You plug in.
You plug in the initial condition now, right? Yeah. We found the building blocks, now we plug in the initial condition. So we plug in x comma 0. So if you plug in x comma 0, that means t is 0. So you just get this. You get c0 plus summation n from 1 through infinity of cn of cosine n pi over 2x. That's what you get from there, and that has to match with 2x minus x squared, right? What is this? This is the Fourier cosine series, right? Yeah. And we know that C0 can be obtained by 1 over L, 0 to L of f of x dx, which in our case is 2x minus x squared dx, with L being 2 and 2, right? And we also did this before, right? What was the value? Was 2/3. If we have L as 2, we did this calculation a few minutes ago. It was 2/3, right? And then how do you get Cn? Well, that's 2 over L, integration from 0 to L of f of x times cosine n pi over Lx dx. And because our function is 2x minus x squared, we replace L by 2. We did this calculation also. I forgot the value. What was it? Oh, that was the negative 8. N squared pi squared?
Yes.
Then negative 1 to the nth power minus what, plus 1?
Yes,
Yeah,
plus 1.
yeah. Okay, so that was the value that we got a few minutes ago. And now, since we got the C0 and Cn, all we have to do is plug them back in here, and that's the final answer. So let's write down the final answer. The answer is uxt equals to 2/3 plus sigma n from 1 through infinity, and then Cn e negative, no, not Cn, it's negative 8 over n squared pi squared, negative 1 to the nth power plus 1 of cosine e of negative 0.2 n squared pi squared t over 4 cosine n pi over 2x. I'm suddenly unsure about this. Did I really have negative 8? Was it negative 8 or positive 8?
Negative.
Negative 8? I hope I'm not wrong. Sounds like it's a bit fishy. Cosine. Oh, cosine goes like that. Let's see. Oh yeah, maybe. Okay, yeah, maybe I'm right. It's not something that a professor should be saying. Yeah, but okay. So this is what you get. Now, let me add another question. So a follow-up question, question 2. What is the equilibrium solution?
Just integral the initial condition and find.
Okay, so you're right. If you take the initial condition, you take the average by integrating this from 0 to 2 and dividing by the length of the interval, which is 2. That's the average value. So that's one way to get it, but we actually did that already, right?
Is it 2 over 3?
It's 2 over 3, right?
Yeah.
But you can read from here. Why?
T goes to infinity.
Yes! That's exactly the answer I wanted. If you take t to infinity of uxt, look what happens. Time goes to infinity, this goes to 0, right? E to the negative infinity is 1 over e to the infinity, which is 0. just quickly goes to 0. So when you send t to infinity, all of this will just disappear. And the only thing that you get is 2/3. So this will be 2/3. That will be the equilibrium solution. So what this says is that if you have this rod with initial condition like that, and you insulate everywhere, and you let the heat equation do its job, at time infinity, everything will be equilibrium. It will be a uniform heat distribution of 2/3. Okay. By the way, if you this has the highest point at 1. So, I mean, this is what is this? This is a 2 minus x times x. So it's it'll be 0 at 0 and 0 at 2. Right? And the highest point will be at 1. It's an upside down parabola. So if you plug in 1, you get 1. So you get this as your initial heat distribution. So wait, so it's 2/3. Oh yeah, it's. Seems to me it has to be 1/3. More. No. More. Okay. Yeah. So if you put at 1/2, you see that more stuff there are more locations that's above 1/2. So the average heat will be above 1/2. Okay. Right. So that's yeah. Okay. So hopefully you didn't just learn the method, but this all made sense physically. You need to have the physical intuition behind all that. But the entire method that we did so far has a name. All this is called separation of variables. Method. And in short, people just say SOV method. And the person who first thought about this was thinking about uxt as a two-dimensional function, right? So here's the time axis, and here's the x from 0 to 2. So initially it has this heat distribution, and then eventually, if you look at the heat distribution, it's a function on this domain. It's a two-dimensional thing. And he realized that, well, this looks rectangular, right? It's a domain that looks rectangular. So the motivation for the separation of variables is that, oh, since it's a rectangular kind of domain, maybe you could come up with solutions that look like a function of x only times a function of t only. And that's where the intuition came up. And what that means is that we're going to do some more complicated cases where the domain is not rectangular like this. When you use Laplace equations, I haven't explained what that is, but in that case, the domain might be circular. In that case, you can't use the separation of variables in the naive way x and y. You have to change that to polar coordinates, and then you can use separation of variables there. So there's some geometry behind this, why it works. Okay? But this thing that we just did is called separation of variables method.